Cool. Okay, so we're in lecture 7. I think practically maybe we're in 8 or 9, but this is the lecture number. So we finished DLG last week, and we did mostly concurrent very shortly. Maybe we'll get back to it someday, but I want to have a full class today for the topic we have now. So I will start today to talk about concurrent collection, not mostly concurrent. And it's going to be snapshot oriented. I will explain why snapshot and what it means and so forth, but this is what it will be. There is one version that we will talk about later in the course, but we're going to go on a few papers. We'll get to it. Okay, let's do it. So the original way to do it was in an old paper. I want to talk about Baum, who did a lot of things for garbage collection, and he's known for doing a lot of garbage collections. He has a garbage collector for C that you can download, and instead of doing malloc and free, you can do gcalloc and gc3 using his library. And people tell me that within 20 minutes you can download it in a big project and just install it and link to it, and it works well. So if you have problems with C, with problems with memory reclamation or any bugs that you have, you can try that. And he's later became more interested in concurrency, and he did a lot of work on threads and processes in C++. He was okay. So we're here. We want to do some concurrent garbage collection, and so we're willing to stop for all the threads in the beginning to start the collection, and the rest should be done concurrently with the threads doing the program work. And we'll later, in the end, like in the second part of this talk, we'll move to on the fly, but we start with concurrent. Okay, so we're talking about snapshot and copy on write, but let's start with a very general idea. So think of this naive collector that stops the program threads. It creates a snapshot. Like a snapshot is like I take a camera and I take a snapshot. I have a picture now that is fixed in time, like it freezes the entire view, and then I can go on. So think of me taking a picture of the heap. In essence, I'm copying all the heap while no one is changing it. So I stop the threads, I copy the entire heap to the side, and then I let the program threads resume, go on working. And then I look at this replica, this copy that I made, and I trace that to find what's unreachable. Okay, once I found what's unreachable, I go to the real heap and I reclaim all these objects. Okay, so this is how I work. It's very, it's like naive. But in general, the main idea here is that if you identify unreachable objects in the replica, you know that they're still unreachable. So no one can touch unreachable objects except for the garbage collector, right? If I want to remind you how it works, there is like unallocated objects, right, that are waiting for, this is the lifetime of an object. First it's unallocated and then the program allocates it. So it's allocated and in the beginning it's reachable, and then it becomes unreachable, which we call dead. And then the GC, it finds all unreachable objects and it brings them to the allocator so the allocator can reallocate them for the program. So the goal is for the GC is to find these unreachable objects and tell the allocator these are ready for allocation. No one needs them anymore. So if you look at all these unreachable objects, no one touches them. The program cannot touch them anymore because they're unreachable. And I'm the collector. I'm the only one who may touch them. So if I take a copy of the heap and freeze its states, and I look for unreachable objects and I identify them, I know that no one touches them except for me. So whatever I find unreachable, I can go on later and say, now let's reclaim these objects. Let's make them unallocated and let the program use them for allocation. So this is the main idea, that garbage, unreachable objects, dead objects are not touched by anyone. And if I find that they have been unreachable 20 years ago, if I didn't make them unallocated, no one touches them. Okay, so I can look at the past, see unreachable objects, and reclaim them. So this is the idea here. The place where the snapshot is taken is here. I stop the program thread, so there's no changes. And then I copy the entire heap. And then this is the time. So I'm saying time, this is a piece of code, right? But I'm saying time because when I execute this code at this time, I can think of the time taking a snapshot. I'm freezing the heap. Okay, what's the problem with this? Why is it naive? Why is it not workable in practice? Yeah.
You have to copy the entire heap.
Right, copying the entire heap is, takes a long time. It's unacceptable. Normally we don't want to copy the entire heap just to trace it. But the good thing is that I can say by locality that not many objects are changed while I do garbage collection. So it's enough to copy only the parts that are modified. So if I could stop the threads, copy the things that are going to be modified while I traverse the heap, and then I could read from the heap anything that's not traversed, that's not modified, right? If it's not modified, I can just read it from the heap. It's the same as it was at snapshot time. If it is modified, I copied it and I can look at the copy. But this seems to require that I'll know the future, right? I need to know what will be changed, which seems wrong. So what I do is I let the program cooperate. So before the program modifies something, it is going to copy the old value before the modification so that I can use it for tracing. So this is the main way that it's going to work. And the first paper suggested to use page protection. So I protect the heap, and in operating systems, you probably heard about protection of pages. You can say I protect, I stop all the mutators, I write protect the memory. No one can write without a trap. Like if anybody tries to write, there's a trap handler that comes to work. And if the program writes something, then the trap handler just copies that page so I can use the old values of this page to do the tracing. So whatever is changed, whichever page changes, I have a copy of the old values of that page, the old pointers that reside on this page that I can trace. And the collector just looks at the heap or the copies. So if a page was not was not copied, then I can just read from the heap. It's the same as it was in the time I started for beginning the collection. And if something was modified, then I have a copy of the values of how it looked when I started the collection. So I can just trace the view as it was when I started. Clear? Any questions? Okay. So when I finish the tracing, I can release all the pages that were copied because I don't need them anymore. I can unprotect all the heap, all the pages of the heap, because I don't want traps to continue happening. I don't need copies anymore. And then I can sweep. And the correctness is, again, if something was unreachable in this snapshot, in what I'm looking at from the past, then it is also not reachable now and I can reclaim it. Okay, the main idea is clear? Okay, cool. So the advantages, it's a very simple concurrent collector, and I don't need to ask for a write barrier and modify the compiler. It is just very easy to implement. Yeah. Who releases the? So the collector, it's doing a tracing like the mark phase. When it finishes the mark phase before doing the sweep, it takes all the copies and releases them, and it also unprotects all the pages of the heap. So if someone writes to the heap now, we don't need a new copy to be made. Yeah.
מה הכוונה שלא צריך light barrier אם כשאני רוצה לשנות ולעשות מודיפיקציה, אני צריך להעתיק את האזור הזה, לעשות לו פרוסט.
Right.
זה לא...
In the way you think of it, it's completely correct that I am doing something with writes. Maybe not with all writes, which is good. Only the first write to the page will do something. The other writes, you will not need to do anything. So from a point of view of like a virtual looking at it, then something happens. But when you actually come to write a garbage collector, your connection to the compiler, to the programming language is sometimes difficult. You have to understand how the compiler works in order to make sure that you have a write barrier. Whenever there is a write of a pointer, you want to have your code executing. And here you don't need to understand the compiler at all. And that's a simplifying condition. It's something that's good for you. You just put a trap handler, and then you don't need to do anything with the compiler. So it is useful, but you're right that conceptually I do have a write barrier, but it's just implemented in the system instead of in the compiler. Yeah. Okay. So the disadvantages is so first of all, this manual protection, usually the system assumes that if there is a trap for a wrong write, then this is a bug. This is not a normal execution. And so usually operating systems do not make an effort to make this very quick. So when I use this mechanism, sometimes it's going to be slow just because it is usually assumed to be like a last resort, a problem with the execution and not a normal execution. And so it's a lot of time inefficient. And the second problem is that I do a trap code. So I write a code for write protection trap, and that is, it's okay if I do it in my own system, in my own computer. But if I am a large company, I am Microsoft, I'm giving you .NET or something, and with it comes something that gets into the trap code of when you run this process. It's not so nice. And also maybe you as the user, you want to write another trap code and you want to install it. Maybe you'll foil my trap code. So it's not very good. We don't like it that it comes with the shipping of a product, something that uses a trap code. Another problem is that usually we do a write barrier when you change a pointer and you want to tell me about it. But here, even if I just change an integer, I increment the counter, the entire page is going to be copied because it changed and the write barrier was trapped, the write protector. And when you do this, you do a whole page. So you copy 4K, in recent systems, it could be 4 megabytes. You just copy all of that because I changed one integer on that page. So that could be costly. And you also need to work with synchronization because if two threads or two threads write to the same page, then you're going to have a problem that you don't want the page to be copied twice, and you don't want, so you want to coordinate between them. You'll need some synchronization. If there's a lot of contention, you'll start having difficulty in running your program. And in general, you write, you increment the counter. Usually it works very fast, and then suddenly it takes a long while to increment the counter because the garbage collector started, and it's something that you cannot anticipate. It's not stable, you're running of the program. So all these things are considered not so nice, and so it's not really used in production these days. One thing that makes it a lot better is the copy on write mechanism. So I hope you studied this in operating system course. This is like when you do a fork, for example, in a Unix system, what you get is you have two processes, and each of them get a copy of the memory, and they are independent. So when one of them makes a change, it doesn't change the other memory. And the way you can do this is just copy the entire memory and give each of them a separate copy. But what you do in practice, you do a copy on write mechanism. Was this something you went to? Okay, great. So the copy on write says, I give them the same space, they share the same practical memory. But when one of them makes a change, then he's going to get a copy of the memory, and the other guy is going to keep the original copy and see what was there in the beginning. So after fork, each one gets a copy of the memory, and we have a copy on write strategy. And when we do that, that is usually implemented very efficiently. This is something that the system really uses as a normal execution. It's not something that's used for debugging or for problems. It's really part of the running your program. So this is done efficiently, and you can use it for garbage collection. The way you do it, when you want to start a garbage collector, the garbage collection cycle, you just fork. Then you have two processes. One of them executes the program, so as normally, as usually you would do, and the other one is going to do the traversal of the heap. And it's going to do a traversal of the heap exactly on how the heap looked when you forked. At that time, he gets a copy of the heap, and whatever the program changes in the heap does not matter to him. He doesn't see any changes. And the system will keep it by a copy on write, but he doesn't know. He just goes over the heap and traverses and see what's reachable, what's unreachable, and then he can have a mark bit table that says what's reachable and what's not, and then he can hand it to the program for a final sweep, which will be done in the process that actually uses the heap. So this is the way to do it with a copy on write. And is it clear? Yeah. Right, there is the program thread and there's the garbage collector thread. When the program thread writes, it has to make his own copy of the page. If he doesn't write, then the system does not do anything. Virtually, the way you look at it is that they get separate copies of the heap. But in practice, it's just copied when the program tries to write. Right. The garbage collector can just look at what, at the shared memory. If nothing was written, then it can just read it.
If it is, if it's the same area as for copy, but for the question. So when the garbage collector collects memory, how does it affect the program if it's right?
So the garbage collector, if you think of it, it never changes the heap, right? So in fact, nothing happens on his side. It just it has this mark bit table that he does, and then he has to somehow transfer it to the program, but he just traces the heap as it was.
Compaction and does
No, this is just mark sweep. Compaction in parallel will be very difficult. We'll talk about it at some point, but we haven't yet. Yeah.
explain to us basically.
This one?
Yes.
So when I mark, I just go over the heap and I mark which object is reachable and which is not. Now, when I'm done with it, I want to also affect the actual heap. I want to reclaim object. That has to be done on the other process, the program process. So you have to deliver it from one process to the other. You have to share a memory in a different way in order to see what another process does. I think this should have been also covered in operating system in the course, but you have to specifically say that this page is going, I will see what the other process is changing. And you have to do it for the mark bit table so the other guy will see what you did. Okay. So this is the copy on write solution, and it also has some problems. So the good thing is you still don't need the compiler support to do the write barrier. You don't need to add page trap code, which we did not want to add when you do a product that you ship. And the system implemented copy on write is usually efficient, but there are bad things. First of all, it's system dependent. Maybe the system you're working on does not do a copy on write, so you fork and suddenly everything is copied. Maybe it's not done efficiently, and then it's not good. And still copy is triggered by integer if you change an integer, and still you have to copy the entire page when an integer changes, and time for writing is unstable. Some of the things we had problems with are still there, even in this manner. Okay, so what we want to do is we want to do it in object level, and we want to do it more targeted at objects of object-oriented program. And this is something that has started with in a paper about reference counting, and then it was continued on mark sweep. We will study the mark sweep first because it's easier to understand it like that, but we'll build some machinery that we can use next week for reference counting. In the way it went in the history, it was first built for reference counting and then used for mark sweep. So this is Yossi Levanoni. Okay, so what is so we're going to talk about these snapshots in an object level logging. So we want to just copy an object before it is modified, and we want no synchronization, all these things that we do not want a compare and swap, a lock, or anything like that. Same thing as Dijkstra did not want that. We want to keep that. There are only reads and writes, and eventually we'll want to make it on the fly. We want to be able to move to very, very short pauses. Okay, so what do you do if you just want to, copy an object before it is modified? This is the simplest thing you can do. If an object, so you have this pointer that you want to point to the object, okay? So you get this, you want to do this right. This pointer should point to this object, and this pointer is inside O. Okay, so you can think of, you have this O, and inside you have some pointer, and you want it to point to obj. Okay, this is a write. I just write a pointer, and this is a write barrier. This is what I will do. So I'm saying I want to copy objects before they're modified, and I will call a modified object dirty. So the first time I am touching this object and modifying it, it is not dirty. And then I copy it. Next time I see it, it will be dirty, and then I don't need to copy it because I already have its values in the snapshot. So this is the most naive way to do it. If the object containing the pointer, this guy, is not dirty, then I know that I have to copy it so that I will be able to trace it the way it was during the snapshot time. So I log all its pointers. I only need its pointers. I don't need integers or other things that are in the object, just pointers. So I log all its pointers and I set it dirty. I tell myself, next time you see it, you don't have to copy it. Okay, and then I can do the actual write. And so this is the most naive way. I mean, the first implementation that you would think of. And the problem with it, so there is a dirty bit per object that tells you if it has been copied or not. Okay, so the problem is that if you have two threads that are doing this, they may write two different values, and then you will not know what was there during the snapshot. So how can it happen? So suppose two threads come to update some pointer on this object, maybe the same pointer or two different pointers, and then they look at the objects and discover that it was not yet copied. It's not dirty. Now they're here. So now they're going to log all the pointers in the object, but one of them is quicker. One of them is faster. It goes, it logs the pointers, set the dirty bit, and changes the object. Now the second one, the slower one, wakes up and it logs the pointers, but this is after the modification. This is not the way it looked when it was snapshotted. Yeah. Yeah. So this thing is changed by the first thread. And then when I log all the pointers here, it is different. So later, when I look at these loggings, I will see two different logs for the same object, and I don't know which one really reflects what was there during the snapshot time and which one is just a different one. I could have more than, yeah, I could have more than two. I could bring three threads here, and I could have three different logs for the same object. So I just don't know which one was during the snapshot. Okay, so what do I do? So I need to solve this, and this is the right barrier that was suggested here. So what you do is you add this. So what do? Before you check if it is dirty, you save all its pointers. You read the pointers and you write them to yourselves. This is the state of the object now. And after that, I check if it's dirty and I do the same things I said before. Why is it good? So let's look at this. So let's look at these two threads are executing this. So it's the same naive write barrier, except that I get the pointers of the object before I check if it's dirty. That's all the difference. And we'll see that it works well. So why does it work well? Suppose two threads find it not dirty and want to log the pointers of this object, right? So if a thread is here and he sees that it's not dirty, then the other thread, what could the other thread do? Once the thread T1 got here, it saw that the object is not dirty, so the other thread could not have been here. So when it checked the if, the other thread could have been here, not after the dirty. So if it was here, then it has not yet changed the pointer because the pointer changes later. So the other thread could be here when this thread checked the object and found it dirty. Now, it read the state of the object before it checked the if condition. So it read it before the other thread did dirty, and so before the other thread has changed it. So it is bound to read the correct value from the snapshot. So just the fact that I read the object state before I checked if it was dirty, gave me the property that all the threads see the state of the object as it was in the snapshot. Okay? Yeah. Okay, what do I do with it? Why? So it's not useful if I don't use it. So what I do with it is when I need to log the state of the object, I don't look at it now as it was in the naive barrier. I take the things that I read before I did the if, before I checked the condition. So when I need to log, I log the things that I read before. Yeah. Right, let's see what happens exactly in the same conditions. So two of them sees the object is not dirty and they want to log its values. So now what can happen? If one of them goes and logs, set the dirty and changes the pointer, this guy already read it will not see the new pointer as it was changed because it read it before. So you can ask, what if it read it after the other guy has changed it? This would be my problem because then I will see something that was not in the snapshot. But if the other guy has changed it, then before that, it set the dirty bit. So there's no chance that I will see the condition as true. So because of this course of event, if both of them are here, then you know that both of them read the original values of the object. You cannot see a new value for the object because once there's a new value for the object by some other thread, the object has to be dirty. It's good that it didn't save the modification. There is like the original value that we want to save, and there are updates, like modifications that we do not want to see. And what this ensures is that we do not see what we read. If we see the object is not dirty, what we read is the values before any change happened. Because the object becomes dirty before it is modified, so if I see it dirty and I've already read its state, then the state has to be before any modification happened concurrently. Okay? Yeah. Right. Exactly. This is the property that we have. If we have several logs, all of them are the same. We know. Right. I need to, when I traverse the heap as a collector, later we will talk about it, I need to find one copy of the object, one logging of the object, and then trace by it. I can just ignore the rest. I can trace again by the rest, but I just ignore it. I use one. Right. Both of them will log the same object, but it will have exactly the same state. You will have two copies of the logs, but it will be the same. So when you trace, you're bound to trace exactly how it was in the snapshot. Make sense? Or so the way let's look at how this buffer looks. So you have a buffer where the objects put the logging, and this will have like which object this is, and then its pointers, and then the next object, and the way Yossi chose to make sure that you know that this is a new record is just he put a one in the lower bit, like the least significant bit of a pointer is always a zero. So he just changed it to one to understand that a new object is being recorded, but you could do whatever you want to make sure you know where is the record of an object. And this is just how it looks. So you may have, for the same object, let's say this is object A, and somewhere you could have object A again. But what you know is that these things are exactly the same. So the pointers are exactly the same. And what you want to do with this information is to trace it. You want to trace it as it was in the snapshot. So you can either trace according to this or according to this. It doesn't matter. You know they're the same. If they were different, if we didn't save the view of the object before we checked the if, then we would have two different things and we would not know which one to traverse, to look at. Yeah. More questions? Yeah.
Like we copy every game in the right area, a bunch of links is not a bit.
Right. It looks too inefficient. Why we copy all the time, and then I can tell you like what we will learn later is that we copy less than 1% of the objects. Most of the objects we see will be dirty already because of locality and because what will happen with new objects. We will talk about this, but this happens like 1% of the time, and 100% of the time we copy this, right? It's not good. It's not efficient. Excellent questions. We'll get to this very soon. Yes, very soon. So it's really excellent. So, so the fact is that most of the updates are to dirty objects. And so when I try to update in a dirty object, I will save a copy in vain. I will not use it ever. And then I will find that the object is dirty and I'll just do the assignment. So I waste time. And so because most updates are to dirty bits, what I'm going to do is I'm going to use a redundant if. So it's going to be like that. I'm going to add a first if that checks if the object is dirty. I will do it twice and it will be redundant. I don't really need this for correctness. But for efficiency, it is very good to do this if. I check if the object is not dirty, and that happens really less than 1% of the time. We'll see the numbers. It could be 1 over 100,000 of the times. And so if it's not dirty, if it is dirty, I just jump to doing the actual assignment. And in the rare cases where it is not dirty, I will do a redundant check again. Okay, I will save the state and then check it again to make it correct. So, excellent question. And, this is how you solve it. Okay. So the logging itself, engineering wise, you can say you can just use a global buffer and just log things. This could be common shared by all threads. And you can also say what Yossi actually did. He said, each thread will have a local buffer where he keeps his things. And so you just take a buffer from a global pool, you get your own small buffer, you make some logging in it. When it's filled, you just take a new buffer, fill it, and so forth. And you have your own local buffers that you don't have to synchronize with anyone to work with these buffers. So, so you get a free buffer, you return a full buffer, and an entry contains an object address and the pointers that are in it. So this is the content of a buffer entry. So the collector can look at any local buffer if it wants in order to trace by its content, or it can actually steal a local buffer. It says, you're the thread, I now take your buffer, get a new one if you want to go on logging stuff. That's what will be needed. Okay. Questions? Okay. So let's look at the collector side. We talked about the write barrier and what the program does to cooperate. Let's look at what the collector does. So it stops all the threads in the beginning, scans all the roots because we don't want to have a write barrier on changes in local pointers. So the roots, there will be no write barrier. I just copy them. I just mark them in the beginning when I stop all the threads. This gives me a flash, like a snapshot of how the local pointers look like. And I also initiate the write barrier for all the threads, and then I let them go on working. And usually the roots, the number of root pointers is small. So it doesn't take me a lot of time to scan the roots. And of course, it doesn't take me a lot of time to tell the threads start doing the write barrier. And now that I can work concurrently with them. So I want to trace, I trace from the roots. I have all these objects directly reachable from the roots. They are now gray. I should go and see what's reachable from them. And whenever I get to a non-dirty object, this means that this object was never changed from the time I stopped the threads. So I can just look at the heap and see its content and then trace its children. So I can do that for all objects that are not dirty. And for objects that are dirty, I just go to the local buffers to where it is logged in the buffer, and I will trace the pointers that are logged in the buffer. So that's like that's how I can trace, and according to a snapshot view of the heap. And when I'm done tracing everything, I will stop the write barrier usage. There is no need to copy to log objects anymore, and I will sweep. So, and then I can clear all buffers, all dirty bits, and be ready for the next garbage collection. Yes.
אנחנו נכנסים לכל העניין של איך אנחנו שומרים את כאילו איך אנחנו מוצאים את האובייקט בלוקל באפר,
Right, excellent question. So how? Okay, but before that, so note that I do the scanning of the roots when I stop the threads because I want to get a snapshot of all the roots values without afterwards monitoring what happens with them. So I don't need to monitor all the local variables. And that is very important. We don't want garbage collectors to have write barriers on local variables. So I just look at them when all the programs do not change anything. And then I see them in the snapshot time. I get their value during snapshot and I don't copy them or I don't do anything with them. Okay, so this is one thing to note. The other thing is the time of the snapshot is here. And again, this is not a time, this is a code. But what happens is when the program gets here, it stops changing the heap until here. And this heap is the heap that I'm taking a snapshot of. So that's why I'm calling it the time of the snapshot. The time of the snapshot is when we get here in the execution of the program. Okay, and now what do I do to find the dirty? So I want the entry for, I have a dirty object and I have to get to its log in order to trace it. What do I do? How do I get to it? So option one, which is what Yossi used, is instead of having a dirty flag that says if the object is dirty or not dirty, like 1 bit, Yossi used a word with a pointer to where the copy is in the buffer. So in the object, you would have a pointer pointing to this buffer entry if the object is logged. If it's not logged, it's null. So not dirty is a null pointer, and dirty is a pointer, non-null pointer, that tells you where the entry, the buffer entry is. So this is a way to get to it when you need to traverse an object, to scan an object. And the option two is you don't keep a pointer, you just keep a bit. Now, when you see, so you go traversing whatever you can from the heap, whatever is non-dirty, you traverse it. All the dirty things, you just keep a list of all the pointers that you could not traverse because they were dirty. And then when you're done, you just take all the buffers until now, you copy them to your own space, the collector, and then it can just find all the places, all the pointers that it wanted to traverse, but it didn't have, they were dirty, so it couldn't use the heap for that. It just goes through the buffer and finds all those that it needs to traverse. So that's the other option. Yossi used this option. And you can think of this as the option that we teach. But if you want to save space and not use a full pointer for the buffers, you can just use a dirty flag and then you're fine. Okay. How do you read? Okay, so we need to take a break. So I will continue with the collector in 10 minutes, 31. Okay. So we want to be able to trace. The garbage collector has to be able to trace. And so this is how you trace an object. Of course, if the object color is not white, it has already been marked, then you don't need to trace it because you have already traced it before. That's like in any tracing. That's the standard thing. So if it is white, then you want to trace it to traverse its children. And so first of all, you shade it. You make it gray to make sure everybody knows it's shaded. And then uh, you want to know the state. You want to know all the pointers that it is pointing to in the time of the snapshot. And you want to traverse its children according to that. So if it's not null, then you know if the object is dirty, it has been copied, and there is a pointer to the entry in the buffers of what the object looked like. So you just go to the buffer and with this dirty object, with this pointer to the buffer entry, and then you copy its values. It's like pointers, how they were, the way they were during the snapshot. Otherwise, now the object is not dirty, and this is the more dangerous thing because you're going to read it from the heap, but at the same time that you read it, maybe the program changes it and copies it. So you have to be careful here. So the object is not dirty. You start by reading it from the heap. And if nothing happens, if the program does not touch it or changes it, then that's fine. You read it and it hasn't been changed, so it's the same view of the object as it was in the snapshot time. So you do that, but after you do that, you make sure if now the program has changed it, then you need to read it again. You have to get it from the buffers because maybe you read the object after it was changed and then it's not as it was in the snapshot time. So in order to make sure you see it as it was in the snapshot time, after you read it from the heap, you check again that the program has not changed it. If it has changed it, then you need to read the copy from the buffer. So after you do that, you now have a copy of the object's pointers as they were during the snapshot time, and you can traverse that. So for each of its children, you can trace it, go back to this same routine with the child. And then you make the color of the object black. You've traversed all its children. It becomes black. You don't need to see children anymore. Okay, so that is fine. This is the collector way of checking how to traverse. And this is, of course, simplified. You don't really want to copy everything all the time, but this is a correct way, and I don't want to start optimizing here and make it more confusing. So there are better ways to do this. So how do you do when you have a new object, you allocate an object, how do you give, what color do you give it and what dirty bit do you set with it? So as usual, during the trace, the object is black because it is like, it is alive and has no children. So basically I can think as if I traversed it and it is fine. And if I'm doing sweep, then like in DLG, I need to give it a gray or white color. And I think you have the color, you had an exercise at homework about doing it more elegantly, which is the right way to do it and the way that everybody does it in production. And if the collector is not active at all, it's not marking, it's not sweeping, then just make it white. And okay, so in terms of the color, it's clear. In terms of whether it's dirty or not, the new objects are always created dirty. And what does dirty mean? Dirty means that they have been copied so that you could traverse them. And for objects that are new, they have no children. You don't need to traverse them anymore. They're black, so you're not going to traverse them. And they can be dirty. I don't need to, next time I change them, I don't need to copy their view as it was in the snapshot. This view was empty. They have no children in the previous snapshots. They were allocated after the snapshot. There was a snapshot time. After that, they were allocated, so there's no view of them during the snapshot time. So I don't need to copy stuff in order to tell myself what this object pointed to during the snapshot. It did not exist in the previous snapshot. So this object is from my point of view dirty. You don't need to copy it for me. I've traversed it. I don't need it anymore. It's dirty. And the fact that it's dirty, so they will not be traced because they're black, the dirty bit. This really lightens the right barrier. So a lot of the changes that I'm doing with new objects. And these new objects are dirty. It means that my right barrier is going to be very light because I'm going to come and check if they're dirty. If not, I'm going to copy them, but all these new objects are already dirty, so I don't need to copy them, and so I will very seldom really copy objects. Usually I will just check if they're dirty and go on my way. So it's going to be very light. Uh, from correctness point of view, so first of all, for progress, I want to make sure that I'm collecting garbage, that I'm not just doing nothing. So I am progressing, because if an object is unreachable before the snapshot time, then no one will trace it. You know, it's not reachable. There's no way to get to it when I look at the snapshot. So it will be reclaimed. And in terms of safety, I want to show that I will not reclaim something that is reachable. So again, all objects that are reachable during the snapshot are going to be marked, because I'm marking according to the snapshot. So it needs to be shown, but for the specific collector, but this is how we designed it, and this is how it works. It just traverses the snapshot. So if something is reachable during the snapshot time, then I will traverse it and see it and mark it. And all those that are unreachable, and I should also say that all new objects, all those created after I took the snapshot, they're going to be black, so I'm not going to reclaim them. And with these two, it means that anything reachable, I will not reclaim. And anything unreachable, they remain unreachable. So I will not, by mistake, reclaim some unreachable objects that became reachable or something like that. Unreachable objects is a steady property. If the collector doesn't make them unallocated, they're going to remain unreachable. The program does not touch them. So I can trust it still unreachable. And therefore I get safety. Okay? So that's the snapshot algorithm. If you have any questions on that. Cool. Okay, so what I want to do now is I want to move to an on-the-fly collector where I don't stop all the threads to create a snapshot in the beginning, but just I want to stop each thread separately, and that is going to become more complicated. But when we moved from Dijkstra to DLG, we were going in a way that we said, you know, this is a problem, let's fix it. This is a problem, let's fix it. Now we think there are no more problems, let's try to prove it. And it was like a non-methodological way to move forward. And I want to do now, this sliding views is a methodology to go from a snapshot algorithm, from a concurrent algorithm, to an on-the-fly algorithm. And if we follow this methodology, we can understand why it's correct, and we know how to do it. And it's going to be a lot clearer, I hope. Also, it will tell you why in the DLG we have these 3 handshakes, why we do mark old and more old than new when we change a pointer in the beginning, and then we mark only the old. All these things that looked mysterious are going to become clear if you understand this methodology of sliding views, how to go from concurrent to on the fly. So just to remind you, concurrent, we're talking about stopping all the threads to make sure everything starts well. What we did here is we collected all the roots, and we started the right barrier at a specific point in time, and that marked the snapshot. After that, anything that changed, we just got a report on what its values were before the change. So it was very easy when we stopped everything and looked at the roots. Here, we're not going to have a monitoring of the roots. We're not going to get all the roots at the same time. So everything is going to be less clear and less organized, but we're going to be able to collect safely with this. So how do we do this? So we want to not stop all the threads simultaneously. Okay, so let's look at the picture. So when we have a snapshot, I do it in a graph like this. I want to say at a specific time of the snapshot, I get everything that I read from the heap, I read at the same time. Like think of these as addresses in the heap. This is the whole heap. And I read anything that I read at the same time. Maybe I'm doing it logically and not specifically going to read everything here, but my view is going to be for at a time t for anything that I read from the heap. And what the sliding views will say, I don't have a specific point in time, but I have an interval, hopefully short. And during this interval between T1 and T2, I will see whatever I read from the heap will be between T1 and T2. So it's going to be not at a specific point, but during an interval that I read the heap. And I will have to make sure that when I use that, I collect safely. I don't reclaim stuff that is reachable, and I make progress and all of that. So this is the view that I'm getting. It's less organized, but I will be able to work with it. And when I show you how I work with it, it will also cover DLG, and it will also cover this move to being on the fly, our algorithm that we specified in the first lecture. We'll get it all on the fly, and it will be methodological. We'll understand what's happening. So if I look at a snapshot, then in a way, so this just says it in a text, right? I say, with a snapshot, I get a view of each object at time t. With the sliding views, I have a time interval, and I get a view of each object in this time interval, but not at a specific point. This says this in a text. And the problem is that you don't have like a snapshot view of the heap. And the danger is if you read stuff, in various points in time, you may lose objects. You will not see that something is reachable. And let's see the most simple example. I'm taking O, and it is reachable from O1, and then I erase it from O1 and put it in O2. Okay, I'm moving it. It's reachable from O1, and then it's reachable from O2. Now with the sliding views, now if I had a snapshot, it's either I see it in O1 or I see it in O2. But if my sliding views sees these objects in different times, I may read O2 here when O is not reachable from it, and I may read O1 here when O is not reachable from it, and then I will see no connection to this O from anywhere, because I just read in different times, different places. So this is the most simplest, it's the simplest example that shows that a sliding view cannot guarantee that I will see O. So I need to do something in order to make it work. I cannot just take a sliding view and say, let's work with that. Let's trace it, and what I see there is that determines what is reachable. So, okay, so what do? What's wrong? We want the snapshot, and what we're going to say, we have a sliding view between T1 and T2, and what we're going to say, we want it to somehow represent a snapshot at time T2. We want to compare what we see with the snapshot at T2. And if we could get to a snapshot at time T2, then we're fine to trace that. But we don't have that. So let's see. What's the difference? So if an object is not modified during all this time, then what the sliding views will read for me will be the same value as the value in T2, which is what I want. I want to see the value in T2. So if it's not modified, that's perfect. If it's modified, let's see how. So modified, I mean, okay. So if it's modified, I can see it somewhere between T1 and T2. I don't know where. So what can happen? So let's look at an object and look at the pointers that are pointing to it and ask, will we see them or not? So if pointers are, so there are four options. There could be pointers deleted and added to it. This is the most general thing. There could be just added to it. This is another option. There could be just deleted pointers to O, and it could be not modified. And like we said, if it's not modified, we're fine. We'll see these pointers because wherever we read, nothing was modified. It's like we read it at time O2, at time T2. So now let's look at the other things. So if we look at if pointers are deleted, then we're going just deleted, nothing was added, then we're going to read these pointers somewhere between T1 and T2. We'll see more pointers than we can see if we just look at T2 because pointers are deleted. So we're in a good state. We have more pointers than the pointers that are pointing to O at T2. So this is great for us. These two are great for us, right? Because pointers that are deleted, we might see them, we might not, but they're not there at T2. The problem is that pointers are added. These are the first two things. So if pointers are added, maybe we don't see them in sliding view, but they do exist in T2, which is a problem for us. Sorry? So deleted is not what I want to have is I want to see all the pointers as they were in T2. So if I read between T1 and T2, I see more pointers. If they're only deleted, I see more pointers. Yeah, I will trace more pointers. That will be fine because I will not miss a reachable object. My goal is to not miss a reachable object. I will not have, a snapshot view, but I will not miss any reachable object. This is my goal. I will see some pointers that are pointing to O that are actually not there in T2, but if I trace them, then I gray O again, or it just makes sure that I see it. So eventually I will have a superset. What I want to have is a superset of all the pointers in T2, like all the set of pointers that are pointing to O in T2, and more maybe that point to O. That's fine if we have more. It will not destroy the safety, not foil our garbage collectors. Maybe we'll see more pointers than we should have seen, but not less. We will not miss reachability of an object. Okay. Yeah. Two is not also bad. Two is also bad. If things are added, I will read it here, but maybe there's more in T2. And I want to have all those that are in T2. So option two is also bad. I have to take care of both. In fact, what I have to make sure that any point that's added, I will see it because it is there in T2 and I may miss it in the sliding views, right? I read somewhere in between T1 and T2, and maybe after I read it, it was added. And so I don't have it, and I want to have it. So can you guess what I will do in order to have all these pointers? Sorry? Yeah. And what will I do in this right barrier? Right? What I want to do is any pointer that's added between T1 and T2, I want to remember it. I will call this a snooping mechanism. Just between T1 and T2, I want to remember any new pointer. And generally, I will work with the same collector that I had. It will just traverse this snapshotted view. But if there is a pointer that was added just between these two T1, T2, then I will record it to myself and it will become like an additional route. I will traverse it whatever happens. This will be for me an object. If it receives the new pointer, then for me it's alive. I'm going to traverse it. Okay, so this goes through all this. Solution. During this interval, I will record the new target of each modified pointer. This is what you suggested, and I will call it snooping. So snooped objects are going to become roots. I'm going to treat them as alive, even if I don't see any other reference to them. So they and their descendants will not be reclaimed. They were reachable between T1 and T2 because the program touched them, but they could be at T2, they could become unreachable, and I will still, yeah. And hopefully T1 and T2 will be a small interval. If it be a huge interval, then yes, I will miss a lot of things that maybe I could reclaim. But if it's small, then okay, yeah, I will keep this, but it will not be too much. And correctness will not be foiled. It's just that I may have floating garbage that I will collect next time. Yeah. Yeah.
I see the case two is problematic, but I don't really see how it would change the reachability. Would it be if an object is reachable from other objects that are in case one, or how do you get?
Right. You could try to analyze it and say like Dijkstra did and say, there's actually no problem, but there are cases with multiple threads, like we did with Dijkstra, when you change pointers, that you get things that you're going to miss. But I cannot. I don't have a prepared example, so I cannot give it to you. But yes, it will not. If you just work with, of course, if you just work with sliding views, you agree that it doesn't work, right? But you're saying what will happen if I just have case two? I'm doing a sliding views and I just have case two, only pointers are added. If you know you're just here, then probably you're fine because you could say, I look at a snapshot at time T1 and what I see in the sliding view is more than that. And then you'll be fine. But if you have both of these, some things are deleted to some and to some objects and to some objects are only added. I don't have like an example I can give you right now, but I suspect it will not work.
Would be the problem if you have
Okay.
case one and case two.
Yeah. Okay. Okay. So snooping, what does it mean? I have the same write barrier as before, but I am going to write a pointer to this object. I'm going to snoop it. I'm going to record to myself, like there will be a list of snooped objects. These are all the objects that receive the new parent, and I'm going to register that to myself. This is just an addition to the write barrier, and I will just this will be a flag that I will put up and down when I need snooping. Okay, so the gain is that we can use the sliding views to safely reclaim garbage. And we safely reclaim garbage because we see a superset of all the pointers in T2. So we have this T1 till T2, T1 till T2. This is time, and we know that we have a super, like we don't read all the heap at T2, but the set of objects, the set of pointers that we see is at least the set of pointers that we would see if we did a snapshot at T2. So we see all the pointers that exist in T2 plus many, maybe some more using this snooping. Okay. So, and the loss that we have is we add the snooping thing to the write barrier, so it's a bit more, it takes a bit more time. And the buffers take space because we snoop objects, and so we need space to register all these objects. But if T1 till T2 is short, then these buffers are not too big and everything is cool. So we need to, this is a motivation to keep T1 till T2 short. This is the motivation. Okay. So the methodology is we start with the snapshot algorithm and relax synchronization. Yeah, question.
בכל מקרה, אבל כאילו בכל מקרה יש לך כאילו מקום שבו אתה שומר את כל הריצ'אבל אובייקטס, לא? כאילו בכל מקרה גם שאתה מסמן את כל האובייקטים שהם reachable, נכון?
Right, I mark all the reachable objects, but I don't, I have a bit per object or bit per word or something like that. Here I need a word per object, right? If I snoop objects, I write the address of an object. I could write it even more than once, but suppose I write it only once, then I will, if I write down the addresses of all reachable objects, it will be a lot of space. It's not like having a bit per object.
אז למה פה אתה לא יכול להשתמש בביט?
I will eventually need to traverse there. I could use a bit table and just have bits all over the heap and mark anything that's snooped. But for that, you know, if I have a short interval, this is going to be a lot more than my buffer. If I'm going to write 100, 1,000 objects out of the millions that we have in the heap, it's going to be a very short interval. If I take a bit table with a bit per object, it's going to take a lot more space. And also later, when I want to go over all the snooped objects and traverse them and their children, I'll have to go through like something proportional to the entire heap space in order to find where I have these ones. So it's a lot better for me to have this buffer. If T1 till T2 is small, then I'll have a short buffer and an easy way to go through all these objects and traverse them. Okay? Okay, cool. So the methodology, I'm going to start with some snapshot algorithm where everything is stopped. I'm going to relax the synchronizations. I'm saying I do not stop all the threads simultaneously now, and let's see what happens. Things will happen badly for sure, but I'm going to now say that any heap object is viewed during some interval. And this I have to show for my algorithm. Each algorithm, it will be different. So the way that what the interval will be and how I will show it. But if I can show that for each object I view it in an interval, and soon we'll do it for our algorithm from the previous hour, if I can show that there is an interval in which I read all objects, then I can go on add snooping and I have a correct algorithm. I will not miss a reachable object. Okay, so this is how I'm going to work. So I'm going to go back to our algorithm from last hour, and I'm going to relax the synchronization, you know, bit by bit. Eventually we'll get to no stopping all threads together. And I will show you that any heap object is going to be viewed during some short interval. After that, I will add snooping, and then we will have working on the fly algorithm. Okay, so here it is. So originally what we said, we'll stop all program threads, we'll scan the roots. We want to create the snapshot logically. So all the roots, we're going to look how they look during the snapshot. We initiate the write barrier to make sure that all the heap will be able to read the way it was in the snapshot. Then we let the threads run. And this is like a stopping time. So we don't want this stopping time. So suppose we could do for each thread, we stop threads and initiate the write barrier usage and allow me to do the roots later, but eventually we'll also do roots reading for each thread separately, so we'll not have to stop all threads simultaneously. And before that, I'm going to start snooping and stop snooping after I resume the threads. I'm going to claim that anything that the collector will see later is going to see between these points, between the points that I start this handshake, where each thread starts the write barrier, and until I finish reading all the roots. I'm going to claim that between these two times, this is T1, this is going to be T2, between these two times, I will get the view of all the objects in the heap. Yeah.
סתם זה כזה, לא יכול להיות שאנחנו גם לא עוצרים אותם בכוונה ביחד, אבל יכול להיות שהם יעצרו במקרה ביחד.
Yeah, I don't mind if they are stopped together. I just don't want to force it. When I force them to stop simultaneously, it's a process. I don't know if I showed it with Yoav presentation. It said it's like 3% of the time, because what happens is you have to stop it not in a write. And so you stop all of the threads, and then you discover three of them are in the middle of the write. So you let these threads go on working, and then you stop them again. Okay, one of them is still in the middle of the... All these things that you make sure that you have all the threads at a good point that you can use takes time. And if each of them just responds and talks to you when it's good for him, then the pauses are going to become a lot smaller. And it matters to me that I don't force them to stop at the same time. I don't mind if they do. So in general, if you remember, I don't remember if I have this slide easily now, but if I have this running program and I want to stop it all at the same time for use with the garbage collector, it will take time. And from Yoav's calculation, it's like 3% of the running time. And if I just say to each of these threads, when you're ready, just cooperate with me. This is the handshake. So, each of them stops. I don't mind if they all stop at the same time, but I just want all of them to cooperate with me. And cooperating here will be the first cooperation will be to initiate the snooping. Second cooperation will be to initiate the write barrier usage, like you're going to start copying stuff. And the third cooperation, which is right now simultaneous stuff, but it will not be, it will be to scan the roots. So whenever it's convenient to you, stop and scan your roots. That is going to be a lot shorter than to wait until all the others can stop at the same time at a good location and scan their roots. Okay. So, okay. So T1 and T2 is going to be before I start doing the write barrier on the first thread. No one is doing the write barrier in T1. And in T2 is everybody is doing the write barrier and everybody is scanned their roots. After that, I'm saying, I'm sure that whatever the collector is going to trace from is going to be between these 2 points. And I need to show this. Okay, this is something that I need to show. Okay, so how do I show this? So I'm going to trace an object. The collector is going to trace an object at some time t3. Okay, it's going to trace it. And the question is, at what time do I trace it? What view do I get? And I have there are two possible cases. One is that this object that I'm tracing, call it A, maybe an object A, I'm tracing it at this time. This is the time, the axis, and I have T1 and T2 as I define them, before I start any write barrier, and after I start all write barriers and scan all roots. This is T1 and T2. And now I want to show you that when I look at an object here, I will see a view that's in between these points. So there are two options. The objects that I'm looking at has been logged until I look at it. Okay? So has it been logged? This object, has it been logged before T3. If it hasn't been logged, then it means that between T2 and T3, it was not modified. Why? Because I said in T2, everyone is running the write barrier. So if anybody is changing anything, it is logging it. So I'm sure at T2 that this is the case. And so if it's not logged, then at least between T2 and T3, it was not modified. If it was not modified and I'm looking at it here, then it's the same view as if I'm looking at it here. It was not modified. So I'm safe. I have it between T1 and T2. I have it at T2, I'm sure. So this is case one. Okay? One. Okay. The case two is that it has been logged. Now, it can be logged. So before T1, there is no write barrier. No one logs. But after T1, the threads are starting to log. And so it can be logged anytime between T1 and T3. And the collector is going to look at this log, right? So at the time where it was logged, this is the time that the collector gets a view of it. So if it was logged between T1 and T2, then perfect. I'm looking at the time between T1 and T2. If it was logged after T2, then what I know is that it's the first time it was modified after T2, because I assumed that at T2 everybody is running the write barrier. So if it would have been modified, like if it is modified between 2 and the time it is logged, then it must be logged earlier. But it was not logged until here. It means that between T2 and the time it is logged, it is not modified. So the view that I can get in the log is similar to the view that's existing at T2. So I can assume that in T2 I would see the same thing, and therefore also something that has been logged after T2, I traverse according to the view at T2. So any object, if it is not logged, fine, I'm looking at the heap here, but it's the same at T2. If it is logged after T2, then I'm looking at the log, but it's the same as T2. If it's logged before T2, it cannot be logged before T1, and I'm looking at this log, and it's just a view between T1 and T2. So there are two things that I'm trusting, that after T1, everybody is using the write barrier, and before T1, no one is using the write barrier. So this says it, the proof relies on no write barrier before T1, and everybody is write barrier after T2. If we go back here, you see that I said T1 is here, and after that, the threads start running the write barrier. So no one is using write barrier before T1, and everybody is using the write barrier before we reach T2. So what I know is that whatever I read, whenever I read it, whether from the heap or from the buffers, it matches the view of this object at some point between T1 and T2. So I've shown you that my algorithm, even if I don't stop all the threads together, but I stop them, whenever they wish with a handshake, I still get a view that each object is read in between T1 and T2. I've showed that for my algorithm, and now it looks like a sliding view between T1 and T2, and I can add snooping and make it correct. And this is what I'm going to do. Any questions on this, showing that I'm reading it between T1 and T2? Okay. So now, you can notice that actually from this point, after the second handshake, so I'm of course adding, the initiating the snooping before anyone starts the write barrier, before T1, and after everybody is running the write barrier, proof that I did will work perfectly. All I needed is that before T1, no one is running the right barrier, and after T2, everybody is running the right barrier. So for any heap pointer, this could be T1 and this could be T2, but there is also the roots that I want to include in the view of the sliding view. So now I want to talk about the roots. So, okay. So first I want to say that in C or C++, I could not do this, okay? Because, I mean, generally, I could not do this because if anyone can move stuff from one root of one thread to another root of another thread, then this cannot work. You can just think that each one is scanning its roots in a different time. Maybe T1 is looking at its roots and it doesn't have a pointer to something. And then at a different time, I go to T2 and look at the roots. And just between that times, I move a pointer from T2 to T1, and then I will not see this pointer. And there's no way I will see it unless I put some monitoring on the roots. And I don't want monitoring of the roots. So if you could, there's no safe on the fly collector. If you could move pointers directly from one thread stack to another. Now, in Java, that is not possible to do that. You cannot write to a stack of another thread. In C, you could do that, but it would require some effort. You know, like a thread would need to look at a local variable. I have this count on my stack, and I put an ampersand to find its address. I write it somewhere on the heap, and then another thread reads from the heap this address and knows where my stack is and can access it. This is not good programming, and it's not something that is done by mistake. So, assuming this does not happen, I want to claim. So it's not possible in Java. It's not considered nice in other languages. Assuming this does not happen, what I want to say, let me get to it. What I want to say that it's enough for me to do a third handshake for marking the roots. So what's happening here? If you look, it's very much like DLG. So DLG says you do one handshake, then you do a second handshake, and then you do a third handshake where you do the roots, where you mark the roots. And between the first and the third, whenever you change a pointer, you mark the old one and the new one, which we call mark the old and snoop. Because of this methodology, it's clear why I have to do both. And after the third handshake, it's enough to mark the old one, which is what we do basically, but it's the same, it goes through the same methodology. I snoop the objects that are modified, so all new targets are recorded, and I do my algorithm to all the other objects. So I have three handshakes like that, and I want to claim that it's okay with the roots. So let's claim that it's okay that I don't do the roots together. Okay, so suppose I want to say, suppose something bad happens. Let's see that it cannot happen. So what could go wrong? So I have some T7 and it reports the roots, it marks the roots at some time in the sliding view. And then T2, at T2, this root is pointing to someone completely different. So maybe I'm going to miss this thing at T2 because I only see this. Okay, I see the things that are given to me from the sliding view, but this root may now be pointing to another object, and maybe this object I will not know. I will not know about it because I read the roots and I don't monitor the changing of the roots. So I don't know that it's now pointing to this O4. I only know that the sliding views told me that it's pointing to O1. But I want to claim that I will know. Why is that? Because what does it mean that I change? So I'm going to do the entire argument about a single pointer. If you have several pointers, you have to do a bit more complex argument about a set of pointer. But suppose T7 has only one pointer. It's the same style of argument, so let's make it simpler. So suppose its root during the sliding views pointed to O1, and in times T2 it points to O4. How did it get to be O4? So the only way to put stuff here is to read them from the heap. So maybe it went to this O1, it read, it cannot go to anywhere except from through his roots. It cannot jump to a random location in the heap. It just reads stuff from its roots. So in order to read anything, it has to go to the heap from its root and read another pointer. And then it can write this pointer instead of its root. So it can go here. And then it can read another thing and write it in his roots. And then it can read another thing and write. It can change his roots many times. All of them are taken from pointers that it reads in the heap. So we have this structure that in the sliding views, I got this object, and there is a path of pointers between this object that I got in the sliding views to the object that's actually there in T2. It has to be like that because that's how a program works. In order to do any change to the root pointer, you have to bring it from somewhere. It could be null, or it could be read from the heap. And so so I see this. Can I not see this? So why will I see all these pointers? So maybe such one of these pointers could exist there throughout, the entire sliding views, and then I will see it because the sliding view will read it. But maybe this pointer was added, and I haven't seen it in the sliding views. It was added later, but because of the snooping, whatever is added, I also see. So I'm bound to see all these pointers, and so I'm bound to see also the object that the roots point to at times t2. And so because of that, I can also read the roots one by one and be okay. So that completes the move to the on-the-fly collector. And now we have a methodology that we've seen example of how to do it in order to get a on-the-fly collector from a snapshot collector, from a one that's concurrent, that you have to stop all the threads for. Cool. So there are ways to optimize the barriers, which I will jump over. I just want to show you the statistics of how many times you get to the right barrier and actually have to copy. These are some benchmarks that Yossi ran. And you see the worst is like less than 1% that you really actually have to copy when you come to the right barrier. Usually you just come to the right barrier, you check the condition, and you just go to the assignment. You do nothing. So that made it very, very fast. From the point of view of the pauses, you could see that a stop the world collector would take hundreds of milliseconds, and this on-the-fly thing would take just milliseconds. It's not a very fair comparison, but it's just, you can see that it's very, very major. It's 2 orders of magnitude. If you look at the throughput, how much you lose because you move to be on the fly, so it depends on how tight the heap, how many garbage collections you have to do. And in the way, so I don't have time to explain more, but usually it's like 10% loss of throughput in a normal circumstances. And so to conclude, you have like a mark sweep garbage collector that you can use Snapshot for concurrency. You can move using the sliding views abstraction. You can move to make it on the fly. And it's fast and it's very, very short pauses. It has very short pauses. Okay, we're in a rush to finish, but we did it. So next week we'll do reference counting. See you then. You can ask me offline. Paul? Okay, so here what you see is that like this is with 8 threads. So with each of these, you get a larger heap and more threads. It's like it's simulating a company that has warehouses, and this is the number of warehouses. And for each warehouse, you get a larger heap and another thread that handles that warehouse. So, yeah. Yeah, I'm sorry, I didn't have time to do it properly, but